Justin, can you do the introduction?
Yeah, sure. This is Julian from CNO. Thank you for speaking. Today he'll be talking about the difficulty of coloring graphs with large girth.
Okay. Thank you so much, Justin, for the introduction. Thank you so much, guys, for inviting me to these combo readings, the classical ones. I'm really glad that this is keeping going in view of the so many things that are happening right now. So I'm really happy to be here. Okay, so what I'm going to talk today is the research that I've been doing with Levent since I was doing my master's, and I mean it's about coloring graphs using this tool, the Nullstellensatz, the Hilbert Nullstellensatz, to transform into hierarchies of system of linear equations, and then you try to see the hardness of coloring graphs with large girth. And this is what we are going to talk today. So before doing that, so let me just go with some motivation. Where are we, or are these what Levent was first interested in these things? So so let me just go with my definition of combinatorial problem. So in this talk, for a combinatorial problem is as follows. So you're given a large set, which is usually implicitly described. Say, I don't know, I have the stable sets of a graph or the colorings of a graph. And then I want to find any specific element of this set with some special attributes. And then this can be like the maximum size stable set, or certain color with certain number of colors. And then so we want to solve this problem. And then this can be done in many different ways, as we know. And we can reformulate it. And usually what we do, at least in CNO, is we map this set X into a large vector space, and then we try to do algebraic stuff or combinatorial stuff to solve the problem. So, and then what we usually do, we map it such that we can find the special element if it is a solution to a system of linear equations, or we can use a linear programming problem, say, and then this linear programming problem is going to output what is this special element in the set X, or we can use a semi-definite programming problem to do this, okay? And then sometimes you actually can do the three of them for a specific problem. Say for the stable set, you can always, I don't know, at least for linear programming, you can always like translate it into semi-definite programming, right? And then this is what happens, right? So system of linear equations, I can describe it as a linear programming. Linear programming, I can describe it as semi-definite programming. And then, so what is the usefulness of this stuff? So the things that we may have with we may have like some additional information if we use, let's say, semi-definite programming, but there is some drawback. So for instance, if we, let's say, if I give you a linear problem, let's say with like, I don't know, 1,000 constraints, then let's say I can formulate that as an SDP, but say also with, let's say I can do it also with 1,000 constraints. So which of these two would you guys pick to solve? Would you use the linear solver or the SDP solver? I guess you guys would say, okay, yes, I should use the linear solver. And it's because of the sophistication of the algorithms, right? So, and then the state of the art of semi-definite programming is not at that point just to solve like many problems that require many constraints or many variables. But at the same time, there is this thing that is interesting, and is this fuzzy line in the plausible size of the formulation. So it may be the case that even though it is harder to solve a semi-definite program with, let's say, 1,000 constraints, maybe it is possible to reduce the size of the formulation in such a way that it becomes now feasible to use semi-definite programming problem. And this is sort of like we want to understand when this happens, right? And then, for instance, there is this famous case of the perfect graph problem, the stable set for perfect graphs. And it's that we know how to solve this using semi-definite programming. We can formulate it using linear programming, but we have no idea how to solve these ones. The formulations that we know for a stable set for perfect graphs for linear programming are usually exponentially large. So semi-definite programming in this case will win, and so on and so forth. So, but today, I'm going to focus on one of these, on one approach, which is using system of linear equations. So this is going to be the talk of today. Yes, so yes, I already said this, and then okay. So what I'm going to do is I'm going to introduce a way to solve the problems, the combinatorial problem, using a hierarchy of system of linear equations, and the way we're going to do it is by using a system of polynomial equations, right? So this is how it's going to be. So I'm giving again the set, and then what I'm going to do is I'm going to formulate it using formulate it using a system of polynomial equations. So that the element X with special attributes that I'm aiming to find is exactly the solution to, is one of the solutions to the system, to a system of polynomial equations like it shows here. Here the K, I mean, this K over here I mean that is a closed algebraic field, otherwise I cannot do the approach that I'm doing, which can be, like said, the complex numbers. So you can think of the complex numbers if you don't know what it's that. Okay, so for instance, but the thing is that this problem is quite hard, right? So this is in generally solving a system of linear equations or polynomial equations. We know that it is quite hard. And for instance, why is it hard? So how would you guys? Let's say I give you an IP of the following form, or I don't know. Let's say I want to solve this system of linear equations like this. I don't know. So this one over here. It's like the solving feasibility of IPs, right? So this is like an IP, right? Well, I need, yeah, that's okay. And then how would you guys encode this using polynomials? So what you can do is simply just use AX equals B, and then you just can introduce the and let's say this is n to the end, then you can do something like this, right? So in this setup, you can actually like solve feasibility of IPs using, if you know how to do an algorithm that solves in general polynomial systems, then you can actually like solve feasibilities for IPs. And then there exist algorithms for this. There is one approach using Grosvenor bases, and then there's another approach using homotopies, which is like this guy over here. This encodes some some algebraic variety, which is like just a surface, and then you just want to make some transformation to these surfaces until you obtain the actual points that solve the system. But okay, so this is in general very, very hard. So how can this be like useful at all? So, and the way we're going to do it is, instead of trying to show how, try to find the X. So let me just think of the core version of the problem. And let me ask, can we verify that the system of polynomial equations doesn't have a solution? And then how would you guys verify if a system doesn't have a solution? So any guys have any ideas? Okay, let me do it easier. Let me do it easier. So let's say I give you a system of linear equations, A equals B, and then you guys want to show that this system doesn't have a solution. So what do you guys do?
Gaussian elimination.
Yeah, you can use Gaussian elimination. That's right. Or you can use some kind of find a certificate for this, and then you can use what is called the Fredholm theorem of the alternative, or Farkas lemma, which is for linear systems. So what you would do is you will try to find a lambda such that when I multiply lambda transpose A on the left-hand side, you obtain equals 0, but on the right-hand side, you obtain equals to 1, right? So certainly, if I can find this lambda over here, I know that this system doesn't have any solution, right? And then this is, I can write this as well as, okay, let's say I want to find lambda transpose A, and then I extend B, and then I want this to be equal to, I don't know, the vector zeros, and then 1. Right, so this is the idea that, so now I tell you this, okay, I can find the certificate. How would you like, guys, how would you like verify that this doesn't have any solution? So it's still a really hard question, I guess. But one way to do it is, okay, I can find multipliers lambda such that I multiply all of these guys and I obtain something that is different from 0, right? Which is the following. So the idea is as follows. So if I can find polynomials a1 to an such that when I multiply a1 times b1, a2 plus times b2, am times bm equals 1, then certainly this system doesn't have a solution, right? Is that clear for everybody? Right, because okay, if it has solution, then I can just plug in the solution here, and then I obtain 0 here, and the right hand side I obtain, right? So as well as Farkas lemma, there is this theorem that actually tells you that this is an if and only if. So you can actually solve. There is no solution for the system of polynomial equations if and only if you can find these polynomials a1 to am. All right, and this is what is called the Hilbert-Nullstellensatz. So this is like a quite like important theorem in algebraic geometry, and it's one of the basic ones. And the proof is not that trivial to do. It requires some work, but it's doable. And then okay, so the elements that are found here, these guys over here, these guys, I'm going to call them certificates, and this is going to be like, these are the main focus of the talk, is to study the size of the certificates, right? Because if I can, so sort of the idea is how hard is to solve this system of linear equations, how hard. So the way I'm going to measure that is I'm going to say, okay, it's hard to verify that this system doesn't have a solution if the degrees of these polynomials are kind of like large. And then, and yes, okay, so this is the idea. So these are called Nullstellensatz certificates. These guys over here are called what I'm going to certificates, and I'm going to study the size of these certificates. And why is this important? Because so this gives us an algorithm to verify if the system doesn't have a solution, and how I run the algorithm. So my algorithm is going to try to find the polynomials a1 to am. And then I'm going to start with a very random guess. I'm going to say, okay, first, let me verify if the AIs, let's suppose that the AIs, all of them have degree 0. So instead of like being polynomials, I have that they are constants. So let's say I have the following system of polynomial equations. I don't know. I'm going to make this out of the blue. I'm sorry. And let's say I have x 1 minus x equals 0, and y 1 minus y equals 0. So this guy over here doesn't have any solution. And then what I can try to find is, okay, I can actually write this as -3 here equals 0. And then I can write down, suppose that there exists maybe coefficients that satisfy this equation and equate to 1. So I can just do, let's say I want to find a1 such that x plus y minus 3 plus a2 x 1 minus x plus a3 y 1 minus y, this guy equals 1. And then I expand this guy over here, and then I equate the equations, and then I equate this both the left hand side and the right hand side, and then what I'm going to obtain is a system of linear equations, and then I'm going to try to solve that system of linear equations. I'm going to see if it has a solution or not. Is that clear? If it has a solution, then I already proved that this system doesn't have any solution. If if it doesn't have any solution, then my next step is I increase the degrees. So what I do is, okay, I assume that it has degree, that the degree of the AIs is 2. Or it's 1, sorry, it's 1. That is the next step, right? and then, so now I'm going, instead of having these guys, I'm going to replace I'm going to add footer variables A1, and then I'm going to repeat the process and then see what happens. And then we know by the Nullstellensatz that these guys over here must exist, right? And then this gives us like a way to use system linear equations to actually solve to actually verify that it doesn't have any solution, the system, the polynomial system. And I'm showing that there is no element in the combinatorial problem that I'm going to find, right? So yeah, so what I was saying is that the good is that the searching for the certificates, it's a linear system equations, and the other thing is that if I can find a certificate, these certificates have a small degree, then my algorithm is going to be effective. And it's going to be quite effective because I'm solving system linear equations. And the other thing is that sometimes I can use finite field computations. So, and then solving system linear equations for when the coefficients are like in a finite field, like sometimes this improves computations, and this can be better. But of course, we know that solving system linear equations is really hard. So the expectation is that this is not going to occur all the time. And in general, the degree of this of the Nullstellensatz certificates. So these guys over here can have degree that is doubly exponential on n, on m, and on the degree of the polynomials pi, which is like garbage. So this is garbage. This is like, we cannot do anything about this. It's not that useful. And the system, even for the small degrees, the system is still like grow very huge. But the hope is that this is for very pathological examples, and then this is for like general system of polynomial equations. But the hope is that for combinatorial problems, and this is work by De Loera, and then the hope is that for combinatorial problems, this maybe the degrees are small. I don't know. That's the hope, and then we can see if this works, and then see what happens. And this is what we were working. So okay, so yeah, so the question is, when is worth this approach? So, and then one of the examples which sort of like seemed to be like nice was with graph coloring. So let me just go back again and make some basic definitions on how can we use this for graph coloring. So I'm giving a graph, and then I'm giving a k, and then I want to determine if the graph is k colorable. And then I want to find a system of polynomial equations that do this, okay? That does this. And then how can I do it? So the key idea, and this is by Bayer, I think it's 82. I have the reference in the next slide, doesn't matter, Bayer. And it's as follows. So, and the final is color using roots of the unity. Then, so what I'm going to do is for each vertex u in the graph, then I'm going to assign a variable xu, and this variable xu is going to be a k root of the unity. So this guy over here satisfies that xu to the k is equal to 1. Right. So I'm in complex numbers. I'm completely in complex numbers now. This is not like even real numbers here. I'm using complex numbers here. All right. And then, so this is easy. And now the next part that I want to verify that if I have an edge, then I want to verify that xu is different from xv, right? And then I want to find a polynomial that encodes this information in some way. How can we do that? So the good thing is the following. So I claim that if I use the following polynomial, given by x u to the k minus 1 plus, no, I can do this here. X u k minus 2 x v plus x v to the k minus 1. I claim that if, is this the polynomial clear at least? Like, you know, what is this? What is this polynomial? The polynomial that I'm trying to write is x u to the k minus x v to the k divided by x u minus x v. Okay. So my claim is that these two guys are different if they are root of the unity. These two guys are different if and only if q is equal to 0. Oh, what is this? What I'm doing? Okay. Oh, sorry. What? Interesting. Okay. And then I want to, so my claim is that this happens if and only this is equal to 0, if and only if these two guys are different. Okay. So at least, do you guys, we can see one of them is really easy. So I think both of them are actually kind of like not hard. So the first one is like, okay, definitely if this is equal to 0, these two guys have to be different. Why? Because suppose that they are the same. Okay, so that's how you do it. So suppose that they are the same. So if xu is equal to xv, then what is I'm going to obtain in this summation over here? So everything here is everything here have the same, like the sum of the degrees of these two variables is always equal to k minus 1. So when I multiply them, what I'm going to obtain is I'm going to obtain k times xu to the k minus 1. And this is going to be equal to 0, right? So this implies that xu is going to be equal to 0, but this is impossible because no root of the unity is equal to 0. So is this part clear for everybody? Yes? Okay. Yes, let me see. How can I see everybody? Let's check. Great. Thank you, Adam. Yes. That is good. That is good. Yeah. All right. But now, what about the other one? The other one is how can I prove the other one? So I want to show that if this is equal to 0, that if this is different, then this has to be equal to 0. And then the way I do it is, okay, suppose that I'm given two roots of the unity that are different. So I know that xu to the k minus x v to the k is equal to what? Both of them are roots of the unity. So I know that this guy over here is equal to 0, right? Because this is equal to 1, both of them. So you cancel out and that's it. And then I can factor this guy out, right? So what is the factorization? Is especially this guy over here. So the factorization is equal to xu minus xv times quuv of x. So if these two guys are different, implies that this element over here is different from 0, and then I have to necessarily have that this polynomial over here has to be equal to 0, and then I'm done. So this is the encoding that we're going to use. Let me write that down in not my horrible scribbles, but maybe let me write it here. So I can formulate graph coloring using this system that I'm showing here. Okay, so this is clear so far. So now I can try to work out if there exists. Okay, this is the explanation, whatever, and then I can try to find. Okay, if G doesn't have a K colorable, then there exists these polynomials over here, the U's and the V's, such that this equation is satisfied, and then I can like run my algorithm, my algorithm of checking if there exists an Nullstellensatz certificate of degree 1, then of degree 2, and then of degree n, etc., to find if it is working. So for this particular system, what do we know? So for this one, what do we know? So this kind of approach for coloring problems were first introduced by Jesus de la Vera, which is a professor at UC Davis. and then what he did is, okay, he studied actually the computational, how is this actually performing computationally. And then what he just studied what happens with the tree coloring problem. And then for the tree coloring problem, you can actually, instead of using the complex numbers, you can actually use computation in F2. And then this allows him to like run the system linear equations like really, really fast. And then he like work out experiments of using like graphs that have like vertices up to like 2,000 vertices and 30,000 edges, which is kind of like interesting. Like you can verify if the graphs are kind of large, and all of the graphs that he tried, there's this DMAX or DIMAX, I don't know how to pronounce that, the competition, like kind of like hard instances of graphs. And then they tried all of those ones, and it turned out that it could verify that most of these ones they could verify. At least the ones that were on this range, they can always verify whether the graph was tree colorable or not. And they also like run random graphs, and then try to see like when a random graphs try to fiddle with the probability so that they are not tree colorable, and then they can always run it. And then they could like sort of, it was like sort of like efficient in those instances. And then this was the thing that was surprising for me when I was first reading this. And they say that, okay, no tree colorable graphs with certificates larger than 4 were found. So it was like really rare to find certificate graphs that needed certificates of degree larger than 4. They have one with degree 7 that needed Nullstellensatz of degree 7, but that was it. Like they had no idea what graphs actually like could need like a certificates of degree 9. And this is why this was interesting for me, because it's surprising, right? That like this is a really, really hard problem, and then these guys come and they're saying that you can actually use like system of linear equations to solve these instances. And then but we don't know like a hard instance for this particular problem. So and this is what I was studying in my master thesis when I was working with Levent. And then okay, this is what I'm okay, sorry, never mind. So first so there is they showed also that they have characterized the ones that need degree 1. By the way, the degrees are always, for k equals 3, the degrees are always of the form 3k plus 1. So the smallest one is degree 1, the next one is degree 4, and the next one is degree 7. That's why I have like these jumps from 4 to 7. It's because that is the smallest degree, because of k equals 3. And then the open question, there's still this open question that we have no idea how to characterize. We know how to characterize the degree 1, but degree 4, we have no idea what are those graphs. Like it's I don't know what is that, and it seems to be hard. I don't know, because they are like a wide range, and then there is some properties. I don't know what properties are happening down there. But then like and then with Levent, this is what I was going with. So with Levent, then we actually showed that if the graph had, for a similar system, it's not the actual system, the Bayer system that I'm showing you, but we could show that if the girth is like greater or equal than 6, then you need degree at least 6 as well. And this is the 6 and 6 here is different from the 7, 4, and 7, because I'm changing the system completely. And this required like I have to look at the matrices and then work around, then try to see something, some pattern in the matrices, and trying to work on like that. But it was quite hard to actually generalize this for general instances. And then 2 years later, these guys, Nauri and Nordstrom, they showed that actually they could find a family of non-calculable graphs that needed large certificates. So now the certificates that they actually needed, they showed that they graphs like needing a certificate that is omega of the number of vertices, which is like the hardest. They are like, it's impossible. It is a really hard for Nullstellensatz, at least. But the issue with this thing is that they don't use any combinatorial properties of the graph themselves. So they are doing this is like a reduction base, like this is like CS type of results that you have this system and then you make a reduction into another system that is well known, that is the pigeonhole principle. And then they have lower bounds into this one, and they transfer the lower bounds for known for those pigeonhole principles to the graph coloring using gadgets and all this stuff. But the question that I'm interested in is, okay, these guys exist, but what are the combinatorial features that the graph actually needs to have high degree certificates? And this is like the question that I'm interested in. Okay, what combinatorial features require? Does the graph needs to like actually be hard for this approach? And then this is what we came up with. What we tried was to actually try to exploit. We can see we can exploit the girth in some way. And then this is what we proved with Levent. So which is the topic of today. So what we show is that we show like it's a certain some. I just predefine the numbers so that they look nice, but it is different, the bound. And so we show basically that if you have a graph that is non-k colorable and it has girth, large girth, say, then you need a degree that is of this order. So the degree, if you want to find the Nullstellensatz degree, the smallest one must be greater than G, sort of G over K plus over 4K. So here what I'm saying is that, okay, at least the degree D must increase with girth. Okay, at least that is the lower bound that we have. So this is not as strong as the result that this Lauria and Ostrom have, because they are finding degrees that are omega of the number of vertices, but graphs that have like large girth, they tend to be like this, and they are not k colorable. The order of them is of order, the number of vertices is of order k to the g. Usually what happens. So the smallest ones are sort of that regimen. So it is actually exponential. So if we see D is going to be logarithm in n somehow, but still we're showing that it has to increase the degree, which was the original question. At least try to find a family that actually increases in that requires large Nullstellensatz certificates, and this is what we were pointing. So this is what we want to what I want to like sort of talk today. Any questions at this point? Okay, great. So how can we find lower bounds? So this is the troll. How do you obtain lower bounds? So again, so the idea is again to use another Farkas lemma type result. Okay, so suppose that
Julian,
yes,
I have like a quick question. So
yes,
can you
sure.
go back to the previous slide? Why is the condition written this way? Like you say G is greater than 2K, and you already look at the ratio G over 4K. Like, is this kind of
yeah, I just wanted that to be like an integer, like but actually I need like larger than 4K, right? I guess.
Yeah.
I don't know.
Does this tell you that like there's no constant sized certificate in some cases, something like that? Like, is that like a consequence of this?
So what do you mean by that? Can you repeat the question? Actually, sorry, Sharat. So there is no.
No, if G is just 2K plus 1.
Oh, no, but my bound is shitty.
Then
That's what it's saying. That's
okay.
the only thing that it's saying, that my bound is really shitty. That I have.
Oh yeah, so the girth has to be like, oh, okay, fine, at least like something a k squared. Yeah.
Yeah. So the girth,
like,
exactly, and then you can see that if the girth has to be actually large for this bound like to be like sort of meaningful. in some sense.
Okay.
Yeah, exactly. Thank you so much. Yes, that's right. Yeah, so I'm assuming in the proofs and everything, I'm assuming that G is sufficiently large. But actually, yes, I think I have to review the proofs that I have. I think my proof works, sort of works with this, but I have to check the numbers. Thank you so much for pointing that out. All right. So okay, so any other questions? We're good. Awesome. Okay. So so how do we get lower bound? So again, so what I was saying is that we can use like a Farkas Farkas lemma type of result as with everything. So we're taking duals and then duals and then duals. And then okay, so suppose that I have a system linear equation that doesn't have a solution, and then I want to show that it doesn't, like, this equation requires the degree to be large enough. Okay, so I want these guys to be large enough. So one of the ideas, and this is how we were working on my master thesis, was like, okay, so I know that if I fix the degree of the AIs, then what is going to happen is that I'm going to obtain a system linear equations, right? So I'm going to obtain these system linear equations, these huge system linear equations A, and then here are the variables x. X are going to be the coefficients of these polynomials, which I'm going to say like a, j, or something like that. A huge vector, and then on the right hand side, I'm going to obtain something of the form 1 and then zeros. So as a certificate is a solution to this system of linear equations. So how can I show that this system of linear equation doesn't have a solution? Well, I use what I was telling you before, which is the Fredholm theorem of the alternative, and I just trying to find some lambdas such that lambda transpose A equals 0, and then lambda transpose this vector 1, 0 equals 1. And this is how you try to do. And then these are like sort of the certificates, and then this gives you another system of linear equations, and then you want to show that system, you want to guarantee that system of linear equations has a solution. And then you can sort of use like the colorings of the graph to plug in these values lambda, and then you kind of work it out. And then but it's going to be a little bit hard to do. It's at least for me, it was hard to actually like try to extract like important information about it. So we were reading these papers, and then we stumbled upon one great idea by Rasborov. And then this idea of Rasborov is actually to use not to use this like linear type of certificate, but actually use the nonlinearity, use the polynomials in some way that actually helps you out. And then so the idea is to find an operator. When I say operator, I mean it's a linear operator. I mean just something that maps polynomials into polynomials. Instead of the lambdas were like mapping monomials into coefficients. This one is actually trying to map polynomials into polynomials. And then so and then we want to do it in such a way that first phi vanishes on the p1 sub to pm. This is the first thing. And then, but it doesn't vanish on 1. Of course, this is what we want. We want to find that guy out that do this. And then we want to make sure that if it is equal to 0 here, I want to make sure that it's sort of also equal to 0 on every sort of corollary of degree up to d of these polynomials over here. And then I can do that by requiring that phi of x to the alpha equals phi of x to phi of x to the alpha. So let me see why this is actually useful. So if I can find a operator that satisfies these conditions over here, then I'm going to show that the AH this AIs over here has to have like degree larger than d. Okay, and then this is sort of like, okay, so what do you do? So what you do is you just plug in the phi over this equation over here. This ugly 5 you apply it over here, and then okay, so you apply it on the left hand side, and then what do you obtain? So So let me do that. So I apply phi here. Dun, dun. Then but linearity is the same as applying 5 to this one, and then 5 to this one, and then 5 to this one, okay? And then what I do is I expand this guy out. I expand this over here. So I have like these ugly multiplications of AI. So I have something like this. So this is my AI, A1, say. And then I have my polynomial P. Say, this is my polynomial P1. And then since if suppose that the degree of the degrees of the I don't know, suppose degree of the AIs is smaller than D. They are equal, I guess. Okay. Suppose that the degrees of these guys is smaller than D. So each of these polynomials over here have degree smaller than D. So again, I use linearity over here, and then I find this is the summation of alphas, and then summation of p alphas, and then I have phi of x alphas, and then let me do betas here. I don't know if I should do this, but okay, anyways. Betas, and then x betas, and then I use this property over here to sort of like pull out all of the x alphas over here one by one. So I know that I can pull out, because of this equation over here, I can sort of like pull out one element at a time, and then I repeat that thing over and over, and then what I'm going to obtain is something of the form like this. I can do something of this form using iteratively this guy over here. And then I collapse back again everything. And then I use linearity again. And then what I'm going to obtain at the end is I'm going to obtain something of the form 5 of A1 times 5 of P1. Okay. And then since this guy over here is equal to 0, everything is going to vanish out, and then all of this guy over here is going to be equal to 0, but on the right hand side is going to be equal to 1. So it's sort of like a shitty explanation, but this is just believe me that this is going to happen if I can find this operator phi that satisfies these conditions over here. Okay. Wow, this is really ugly. Okay. Okay, so then now the idea is, okay, nice. You this is one way, but how can you actually define that operator? And this is the hardest part here. So now how do you do it? So the idea, again, as an idea of Rasberov, is to actually define the operator locally. So so what do I mean by that? So what I'm going to do is, instead of like defining it globally, so what I'm going to define it for each particular monomial of degree at most D, or for each particular monomial of degree at most D, yes. And then for the rest, I'm going to set up equal to 0. And then the way I'm going to do it is that I'm going to choose you're going to give me a monomial alpha. And then I'm going to select a subset of the polynomials pi that are related to that guy. So I'm going to choose, let's say, P1, PI1, and then PIN, something like that. I'm going to choose a subset of those polynomials. And then I'm going to define phi of alpha using these polynomials over here. And how use them, the way I'm going to do it is going to be as follows. So the basic idea that I'm going to do is I'm going to take x to the alpha, and then I'm going to divide by these polynomials. Divide by these polynomials, and then define phi the x to the alpha as the remainder of the division. Okay, and this is how would you can sort of define it. And the reason why would you do that is because it is this, if you do this, it is going to satisfy this condition over here. This condition over here is going to satisfy for free, locally at least.
So Julian, when you say
Yes.
divide, then do you divide with all of them, or?
Yes, so that is an interesting question, because of course we know how to divide two polynomials, but how do you divide one polynomial against many polynomials? So for this one I need to introduce more stuff, because okay, so because this is multivariate stuff, right? So how do you do that? So this is what I'm saying, reducing. This is what I mean by reducing. I'm going to explain this in a second, Sharat. So by reducing, I mean I take the monomial, and then I divide by all of them, and then I take the remainder. And this is reducing. I'm reducing modulo the polynomials p1 up to pi m, whatever. That's it. I choose. Okay. And then for that, I need to define to you what is an ideal. Okay. So let me just create a new page here. Okay. So okay. So how do I describe this? Okay, so yeah, so okay, so the idea is to, let me just write that again. The idea is to define x to the alpha equals to remainder of division by this guy over here, by some polynomials that I choose, some particular set of polynomials, also polynomials. Okay. And then how is this division divided? So how do you divide two polynomials how do you divide two polynomials? So how do you do that? I remember. So how do you do that? So you take a polynomial p, and then you sort of try to multiply by the highest degree polynomial that you have. You have a polynomial q, right? And then you sort of try to cancel out the largest. So the way that I do this is you're giving me these two polynomials, and then I just do cancel the largest monomial in F using Q, in P using Q, right? So for instance, how do you divide x3 plus x plus 1 divided by the polynomial x plus 1? I don't know. So the thing that you do is you cancel, you try to first eliminate this guy over here, which is the largest one, right? So you multiply it by x squared, x plus 1, and then you subtract this guy over here, right? This is what you do in one variable calculus, in one variables. But when you have many variables, you have to define an order of the monomials, because now our polynomials look like that, like the following. So let's say I have three polynomials. So I have x, y plus x z, and then I want, let's say, to divide it by x z plus x squared or something like that. And then you want to divide this polynomial by this polynomial. So how do you do that? So I don't know which one is larger. Which of these two are larger than? Which is larger, this guy or this guy? I don't have like a proper ordering here. So what you have to do is you define first an ordering of the monomials, and then the order that we usually choose for this type of set is called the greater lexicographic order, standing for graded lexicographic order. And then this is like that follows. So let's say I have x, it's greater than y greater than z. So the first thing that I'm going to do is let's say I'm giving two monomials. I don't know, x y alpha 2 and z alpha 3, and then I'm giving the monomial x beta 1 y beta 2 and z beta 3. So what you do is you first check which one has the highest degree. So the one that has the largest degree is certainly greater than the other one, right? So the first thing that you check is you check if alpha 1 plus alpha 2 plus alpha 3 is greater or equal than beta 1 plus beta 2 plus beta 3. And then the next thing, if the two of them are the same, if the summation are the same, then you start comparing lexicographically. So you start comparing. Okay, so x here is the greatest variable. So I'm going to compare the degree of x alpha 1 and the degree of x beta 1. So if alpha 1 is larger than beta 1, then I choose this guy to be larger than the other one. If they are the same, then I continue with the next one. Okay, is that clear? Is this clear? Is this like very, very trivial? Or not very, very trivial, but at least it's clear, Sharad?
Yeah.
Yeah. Okay. So I have to define this, and then using that ordering, I can sort of like define the division in that way. So I just and then you cannot do it like right from the bat. What you can do, you start dividing one polynomial by one polynomial. You start dividing by the first polynomial, then by the second. If you want to divide, let's say, by many polynomials, you divide by the first polynomial first, and then the result you divide by the second polynomial, and like the remainder, and so on until the last polynomial. Okay, but this depends on the order for general polynomials. So this is going to actually depend on the order. So the division is actually not going to be like as usual as we wanted. So what you have to do is you need to reduce the polynomials P1 to Pn to something that is called a Grobner basis. And with this Grobner basis, you divide the polynomial and you actually always obtain a unique result. Okay. I know this is like many things, but just believe me that I can do that division in such a way that it's going to give me a unique one, and the way I'm going to do it is by finding a Grobner basis of the polynomials P1 up to Pm. So I find a Grobner basis. And divide. Okay. I find a Grobner basis of the ideal P1 up to Pn, and then use that Grobner basis to actually define the polynomial. And then I take what is the remainder of that one. Okay. And then let me just make a last definition here. So this guys over here, do we know? So this guy over here, when I say that this is an ideal. So what I say an ideal is just simply an idea of polynomials is just all possible polynomial combinations of that, guys. It's like the span. It's like the span, but in polynomial version. That is an ideal. And then what I'm trying to do, what is the reduction trying to do, is this 5, the remainder. So 5, what it's doing is 5 of a monomial. What it's doing is trying to find a polynomial in this ideal. No, it's okay. So 5, yeah. What it's doing? No, I want to say it differently. I want to say something different. Never mind. So what I'm trying to do is I'm going to try to find a polynomial in this ideal, say a polynomial Q, such that the largest element is x to the alpha, and then I have some elements that are sort of irreducible. And phi of x, what is going to be, so when I divide this polynomial by this, since this is in the ideal, so what I'm going to obtain is this remainder over here, which is r of x. This is sort of what is going to happen. I'm doing really bad explanation here, but bear with me. So this is just, there is a way to define division by polynomials using the Euclidean algorithm and using like by first reducing the polynomials that they are giving to us, and then I take the remainder of that guy, and that remainder is the actual how I define my operator phi. And then I want to make some specific, I want to do some definition, and it's the following. So I say that a monomial, so I'm giving an ideal I generated, say, by the polynomials P1 up to Pm. And I'm giving a monomial x to the alpha. So I say that x alpha is irreducible modulo I if, oh shit, if the division is actually the same guy. So I cannot reduce the guy. I cannot reduce anything. So that's meaning irreducible. So meaning that 5, when I define 5 on this polynomial, say on x to the alpha, I obtain x to the alpha. Okay. So this is irreducible. This is the something that I want to state. So x to the alpha is irreducible, and everything transform into stating whether one monomial is irreducible with respect some basis. I'm going to go to this later, but okay. So this is sort of like I'm going to define it. So how I'm going to do that in the graph setup. So I want sort of like I want to find this phi. And then what I'm going to try to do is try to find which polynomials to assign for a monomial. See, they give me a monomial, and then I'm going to try to find a subset of the polynomials pi. In my setup for the graph case, so we are given the following polynomial. So this is the polynomials of my system in the graph scenario. And then I have to give some order to the monomials. So I have to use ordering. So what I'm going to use is just use the labels of I'm going to label the vertices of the graph. And then I'm going to define one variable to be larger than the other if they are like, if the indexes that I given in the graph are actually like one is smaller than the other. And then with this order, now I can define division between monomials with this precise order of the graph. So the graph is sort of giving the order. And then when I'm doing the proof, I'm actually using that I'm using a k+1 colorability of the graph. I use it explicitly to define a specific order. So not any order works for me. I'm going to actually find that guy over there. And then okay. So how much I ran out of time? Is that what I think happened?
No, we started kind of late. You can keep going if you're near the end.
Okay, wait. Okay, whatever. So okay. So and then what I'm going to do is so I'm giving a monomial. I'm going to assign a subset of these polynomials over here. And this subset of polynomials, I'm going to sort of forget about these guys because these guys are like, I don't care about these guys. These are just like telling me that they are roots of the unity. I can just disregard these guys over here. And then I'm going to do everything modulo this ideal. But okay, it doesn't matter here. So what I'm going to do is I'm going to, for each monomial that you give me, oh, Jesus Christ. For each monomial that you give me, I'm going to define a subgraph. So each of these polynomials correspond to an edge, okay? Each of these polynomials corresponds to an edge, and then what I'm going to do is I'm going to find a subset of those edges. So this is going to be as a subgraph for each x to the alpha. And using that subgraphs, I'm going to define the phi sub alpha, and then that is how the proof more or less is going to go. And then the next thing is how can I choose these graphs G sub alpha, which is like, okay, how the heck, how do you actually choose those guys? And the way is that the ultimate goal was to understand what was the meaning of irreducibility for in a graph. So saying that I'm giving you x to the alpha, and then I'm giving you the polynomials p sub q sub uv for some subgraph g sub alpha. And then I want to ask when x to the alpha is irreducible modulo, let me call this is like G alpha at the end, it's just the edges, modulo G alpha. And this is the question that I want to study at the end. So if I sort of understand what does it mean if I'm giving this monomial over here, if I can actually abstract what does it mean to be irreducible modulo like some subgraph, then I sort of like kind of a handle, and then I can show the theorem. And that was the general idea. I want to understand that thing over here. So, and the way to understand it, so anyway, so here I'm saying that the G alpha, I choose it in such a way that it satisfies some properties that are important for me. But I want to talk about like how to actually define the G alpha. So I want to understand theorem says the following. So suppose ¿tienes internet? Sí. I don't know. Hello. Yes.
Oh, yeah.
Yeah, I'm back. Okay. I'm sorry. Okay. Great.
Oh, I thought it was my internet, which was spotty.
No. It was. I think it's
Okay.
mine because it says that connection unstable. I guess it was mine.
Okay.
So are we here? All of us are here, I guess.
Yeah.
Yeah, I think
Okay.
so.
Great. Okay. So the next thing is everything reduces to understand when is a monomial irreducible. So when is that when I divide by these polynomials, I obtain the same monomial. And the way to do it is instead of working, my work is with glex, but just to get an idea of what happens, I'm going to use with just the lex ordering instead. So I'm going to try to study when a monomial is irreducible with certain ideal, but with the ordering lex. In lex ordering, I'm just using this the second. I'm not looking at the total degree, but I'm just looking at, for instance, this variable over here is going to be larger than y to the 5 if y is greater than y. So I'm not considering any degree here for this game. And then this is not the actual proof that I use. I have to change the proof completely because this doesn't work, but this is sort of the inspiration. So, and then the inspiration is the thing goes as follows. So I'm giving x to the alpha, and I'm giving a subset of edges of the graph. Okay. And then I want to ask, when is x to the alpha irreducible modulo the ideal generated by f, by the edges f. And by this, I mean the polynomials q, uv such that uv is in f, okay? This ideal. So I want to study that. And then there is this beautiful theorem that actually transforms this into a game. And the game is as follows. So I have Bob and Alice. Bob know they know all the colorings of the graph. Okay. And then Bob secretly chooses a coloring. Okay. He select, let's say I'm giving this graph over here, and then Bob secretly chooses a coloring. And then Bob is going to give Alice the opportunity to guess what is the color that he chooses for each of the vertices. If Alice managed to guess at least one of the colors, then Alice wins. This is sort of what is the game about. And but Bob is going to give you some certain number of opportunities for each node of the graph. So he first order the vertices of the graph that is shown here. So all the vertices are ordered in this form. So 1 up to 10. And then Bob is going to look up the monomial. So but we have the monomial, and the monomial, well, the monomial has variables x1 to x10. And let's say I have some alpha 10 here and some alpha 1 here. And then Bob is going to give Alice alpha 10 times guesses to, so she can guess alpha 10 times the color for this vertex. Okay. So let's say the color for this vertex is let's say, oh, Jesus Christ. Let's say alpha, yeah. So let's say I'm giving, let's say alpha 10 is equal to 2, say. So here's 2. So Bob is going to give 2 chances of to Alice to guess what is this color. So, and let's say I'm using 3 colors, say here. So then for instance, Alice can guess or not, right? So Bob, what is going to do is, okay, ask Alice, which is this color? And Alice is going to say, okay, it's blue. And he's going to say, no, it's not blue. And then you go with the next one, it's red. Alice asks if it is red or not. And then Bob says, no, it's not red. It's actually green. And then he shows the color to Alice. And then he shows the color to Alice. Just. So it's just actually green. And now he goes with the next vertex. And then again, let's say I have a 1 here. And then I give Alice 1 opportunity to guess that color. And then if Alice doesn't come up with a solution, so he actually paints the color, right? So for instance, here, now Alice gets some extra information. Because now Alice knows that this color is not green and it's not red, right? So if Bob gives two opportunities to Alice here, then she can actually guess the color, right? Is that okay? One opportunity, I think, right?
Like, why do you even need like an opportunity? You can just like be sure that it is.
Oh yeah, you know that it's actually, yes, you don't even need an opportunity. Yeah. You're right. Yeah. You're right. Yeah. You're pretty sure that it's going to be, it has to be blue, right?
Yeah.
And then Alice wins the game. Okay. If Alice wins the game, then the monomial is reducible. Okay. And then this sort of give me some idea of how to construct the G alphas. Is that at least is the game clear? So for instance, is X1 reducible modulo the graph above? So what do you guys say?
So we can know the color for X1.
So Alice has to guess in order to win the game. Alice has to like guess what is the color of the vertices of the first vertex. And she has 2 chances, right?
Yeah, that's the only thing that she can do, because she cannot ask any questions regarding other vertices, right?
Yeah, but then Bob has to show, because she didn't give any opportunities to Alice, right? So since Bob didn't give any opportunities to Alice to guess the 10, he actually has to show what is the color.
Oh,
okay. So he actually has to ask what is this color over here, and then again, Bob didn't give any solution for the second one, so he has to actually show what is the color for the second one, and then from here they have to color this with some color, right? Bob has to give some colors to this guy. So Alice is always going to be able to know what is that color, right? Because there's only 2 colors left, at least in this example, right? But she always has a strategy to win. So since she always has a strategy to win, then this monomial is going to be reducible. And then this is where I use like sort of this knowledge to actually describe what were the graphs G alpha. So what I did was like, okay, so I start with a monomial. And for instance, what happens if I change the graph a little bit and then I put something like something here? But it doesn't make any sense here. I have to prepare this in advance. I'm sorry. If I put another vertex below this one, no, that doesn't work for me. Never mind. So I used like sort of this information to guess what is the graph that I needed, and then the graph that I needed was actually the first thing that I do is I look at the monomial x to the alpha, and then I look at the support of this monomial. So this guy over here, let's say this guy is x1 to the 2, x2 to the 3, and x4. Say I don't know, and I look at where are those vertices, okay? And then I choose all descendants of those guys, so all childs of these guys, because these are ordered, right? So the vertices are ordered, and I choose all of the descendants. And then after choosing all of the descendants, I make some extra operations, like if they have a pairing in common, then I join them, and then I sort of create this graph. And then using that graph, I define the operator, and that's how more or less goes the stuff.
So they play this game and then determine whether something is like reducible or not.
Reducible or not, and then using that information, I sort of like I kind of like tell whether reducibility. What happens if I add another edge, right? Because the problem here is that I'm defining the phi. The way I'm defining the phi is like it has this third property, which is like ugly. Like this third property is the more troublesome, right? Because I'm defining the graph locally, okay? So I'm defining the phi locally, right? So I am defining the first, let's say this 5. Jesus Christ, what happens? Okay. This phi over here is defined with respect to this guy over here. So this monomial corresponds to some subgraph. Then let me call it G1. And then this is another alpha. So this guy over here is going to depend on another graph G2. And I want this to be sort of compatible, meaning that I want, and then what I want is that if x beta to be irreducible, if and only if it is irreducible with respect to this other graph. And then how do I check irreducibility on both of them? Using the Lex game. And then this is how it's done. And then since it is equal, it is irreducible with respect G1 and G2, then this sort of condition is going to be satisfied, and then I'm going to be done. That's sort of idea, but it's kind of hard to explain in these short minutes. But okay, that is sort of clarifies your question, Sharat.
Yeah.
Okay. And then that's it. Then I run the proof, and then it sort of works out how I just the operator. You just show that the operator works, and then that's it. What else can I say here? Yeah, and that's it. And then open questions is just we just want to find the next step is just find interesting classes where the Nullstellensatz actually is efficient, because all of these are like negative results. Like if it has large girth, it is actually not good. Or if it is like an expander this way, it is not good. Or but then what happens with for instance perfect graphs? So can we, maybe this can be used to detect if a perfect graph has a certain chromatic number. We don't know anything about that. And the other one, okay, the ones that I already told you, which is characterized graphs that have large degree, certificate of degree at most 4. And then the other thing is to improve the bound, because our bounds are like sort of like logarithm in the size of the graph. But yeah, so we are looking into that. And that's it. That's it. Thank you so much. Sorry for the length of the talk. Thank you.
Yeah, let's thank Julian for the talk.
Okay. Thank you.
Okay. Right. So questions for Julian.
Can you hear me?
Yeah.
When you play the Lex game, do you start from the vertex with the highest priority?
Yes. No, with the highest. Yeah, with the highest index, right? So all the vertices are with the highest index. Yes, you start the game with that one. Yeah.
So for example, like you show that x1 square is irreducible.
It's reducible.
It's reducible, but x10 square would be irreducible.
Yes, exactly. X10 square would be irreducible because yes,
you have no information.
Alice has no information, and then yeah. So it is sort of like this. So you can check it by using these long divisions and then trying to define with all of these things, and then actually you can do it this way, which is way more easier. So it just facilitates times a lot. Yeah. So that's why it's like kind of interesting for me at least. Yes.
But shouldn't x10 squared be sorry, you can determine, right? Like you ask 2 questions and then you know for sure what.
No, because you have 3 colors, right?
Yeah, but like when you know 2 are not not possible, the third one is.
But Alice only has 2 choices. You have 3 colors and she only has to choose 2 guesses, 2 possible guesses, right? So Bob says, okay, so
oh, right. Sure. Okay. Yeah. One of the guesses, it's not just about knowing the answer. It's about like, actually guessing the, okay.
Yeah. One of the answers has to be like, okay, I guessed that completely. And then you jump. And then this is sort of like you detect these algebraic informations in this game. Yeah.
And sorry, I have another question. Why did you assume that the graph is k+1 colorable? Is that assumption crucial?
Yeah, it is crucial, but I mean, it's not crucial because if you have that that has chromatic number k+1, I just choose a subgraph, and then I work with that subgraph. I choose a subgraph that has chromatic number k+1.
Oh, because you're trying to show lower bounds, right?
Yeah. Exactly. So I just use that subgraph, and then the other part that is crucial is how I'm ordering the vertices. The ordering depends of the coloring. So if I'm using the coloring strictly no any order works to actually to make all these terms work. So you actually need to find a special ordering, and the ordering that I'm doing is very easy. I just take a coloring of the graph. I just take a coloring of the graph, and then I say red are larger than, this is not red. Okay, so I say all the guys that are red are always going to be larger than all the guys that are, say, green. And then what I do is I enumerate, and then this is larger than the guys that are blue, say. Oh, shoots. And then what I do, I first enumerate these guys over here. So I look at the coloring, and then I first enumerate from 1 to the number of those guys using this color, blue. And then I enumerate the next one using this color. And then I enumerate the next one, this color. And then what I'm going to do is the graphs, the way I'm going to define it is I'm giving a monomial. And then with that monomial, I look all possible, like, childs of those vertices. Child meaning that one index is that the index is actually smaller than the other one. Okay, and then I look at those graphs. If I do this in this way, the graphs, and the graph has large girth, then these graphs are always going to be forests. So the graphs G alpha that I'm going to choose are always going to be forest, and that is when the bound is coming from. The bound is actually just coming from that sort of information of I want these guys to be like trees, and then what is the smallest degree D that I can ensure so that these graphs are always like trees, and then or forests, and then I use the forest thing to actually like just to make the coloring easier. And that's it. Yes. Thank you.
Any other questions? Okay. Let's thank Julian again.
All right. Thank you so much, guys. Thank you so much for the invitation.
Okay. So next week we won't have a